Good morning. Okay, so now we're going to talk about molecular bonds. So the first bond between two atoms is called a sigma bond. It's the overlap of the orbitals. Okay, so let me just show you hydrogen. Here's hydrogen. Here's hydrogen. As they move closer together, there gets to be a point where the two orbitals overlap. This is a sigma bond. Now, what are the properties? One, if you look at the axis on which my nuclei are aligned with, my sigma bond is in line with the axis of the nuclei. Okay, now why is this important? This is important because then I can rotate, I can spin around my sigma bond freely. Okay, so this means I get free rotation. In other words, free being not requiring a lot of energy. Free rotation around a sigma bond. Well, when you look at something like hydrogen, you're not going to really be able to tell too much of a difference. So let's do a sigma bond between two carbons. So if we look at something like ethane, okay, and we're going to focus actually on this sigma bond, okay, so we know I'm not going to draw the rest, but based on the structure that we have here, you know this is an sp3 sigma bond. Okay, and what I'm going to do is I'm going to draw the rest of my hydrogens like this instead of using the bubbles. And let me show you why. Because if I rotate, let's say, suppose I rotate this 180 degrees. Then I still have my carbon. Still have my carbon. Okay. So I'll keep the green side the same. The red side, I'll draw what it looks like after I rotate it 180 degrees. Okay, so that's after rotation. Notice, however, these compounds are exactly the same. Not a big surprise there, is that? And just so you know, how do we differentiate between these two? The only difference between these two is the location of the hydrogens. One is in the same plane here. This one, the same plane is this way. When I have all these different structures, okay, based on free rotation around a sigma bond, these are called conformers. Okay, you can guess you have an infinite number of conformers as you're spinning around the single bond. Okay, so these are your sigma bonds. First bond. What happens if you have multiple bonds? It turns out your double bond and your triple bonds after the first bond, which we know now is a sigma bond, the rest are pi bonds. And why pi? Because they are overlaps of p orbitals. So the previous structure, ethane, doesn't have any p orbitals. Everything's sp3. So when you look for double and triple bonds, bear in mind, for the hybridization state, we're looking at sp or sp2. You can't have pi bonds with sp3. Okay? So if we do that, let's take a look at what happens. We're going to look at this molecule. Ethene. Okay. These are sp2 hybridized. So if I draw the carbons, okay, so these carbons are sp2 hybridized. So let's first draw our sigma bond. So here's my carbon. And I don't know if this drawing conveys it or not, but if you look, these should be a little bit less long than the sp3 because they have more s character to it. So that's my sp2, and then what I'm going to do is I'm going to draw, I'm going to take this, I'm going to rotate it 90 degrees, just the molecule, not the bond, just so it's a little easier to see the p orbital. So if I do that, then my p orbitals are going to be in the plane of the board. Okay? So a pi bond actually is the overlap of this. Okay? And one pi bond almost looks like a tooth here. So one pi bond consists, it's overlap above and below the plane, the axis. Okay, that's one pi bond. So in here, above and below, we're just looking at electron density. I have 2 electrons. Okay? What are the ramifications of this? The ramifications of this is that in a pi bond, okay, there's no free rotation. Okay, so what I mean by no free rotation. So let's draw trans-2-butene and cis-2-butene. If I draw this out, like I had in the previous picture, so again, rotate this 90 degrees. So this one, stays out, hydrogen is out, going back, CH3, going back, H. If you draw your pi bond, since I have to have these overlap, then to rotate, what would happen is I would get something like this. So, this p orbital is right here. But if I rotate this, then the p orbital here, okay, up here is H, down there is CH3. So now, I no longer have them overlap. They're basically, this is in the plane of the board, this one's coming out of the plane of the board like that. And there's really no overlap whatsoever. So this is a broken pi bond. So to go through and rotate and break a pi bond requires energy. And quite a bit. So instead what happens is we have two different compounds then. We have a compound where you have this orientation, and we have a compound with this orientation. But there's no free rotation around this to go from here to here, like you would see with a single bond. Because of that, we have two completely different structures, okay? These are two different compounds. All right, so how are they related? We call these two different compounds. They have the same molecular formula. The only difference is their orientation of these methyl groups in space. So these are actually stereoisomers, and since there's a number of different types of stereoisomers, we actually call them geometric isomers. Their geometry is different. Okay? When the groups we have similar groups on opposite sides, of the double bond. We call this trans. similar groups. On the same side of the double bond. We call that cis. Okay? So, for example, besides these two, this is a cis compound. And this is a trans compound. Being different compounds, they have different properties. Okay, so melting point, boiling point, these are different in toxicity too. This is fairly safe to consume. Not that you'd want to go out and eat a whole bunch, but if you do eat some, if we have it in a drug, you're fine with that. This one isn't so good for you. So toxicity is also different. So these are examples. Okay, so that's our bonding. Now let's talk about a triple bond. Double bonds are significant because there is no free rotation. What about a triple bond? Is there free rotation? Well, let's take a look at something like okay, I'm going to focus on that bond, of course. Here's my carbon. Here's my carbon. Okay, I made them squatter because this is sp-sp, sigma. Okay, and on this side, I'm just going to draw the line. This side I have a carbon. Okay, now what about my p orbitals? So it's going to get a little messy. I'll use different colors. In the plane of the board, I have this p orbital. Okay. Coming out of the plane of the board, so you have that one. So in other words, I have electron density here, and that's one pi bond. And here I have my second pi bond. So you can have two pi bonds. Well, if you look at it, if I start to rotate, okay, the maximum difference is here before it lines up in the plane of the board here, and I reform my pi bond. So you really don't get a significant drop in energy or requirement of energy in order to break one pi bond to reform the next because there's enough overlap. The other thing is with this free rotation is that it's symmetrical, it's linear, okay? So triple bonds can freely rotate. Okay. And that's because we don't break your pi bond past 45 degrees. Okay? So those are all your multiple bonds. And if you have just a single bond, the first bond in a single bond, double bond, triple bond, they're always a sigma bond. Then if you have a double or triple, any additional lines, any additional bonds, those are all going to be pi bonds. Well, hybridization is very important, and we invoke it a lot in trying to understand what's happening with the geometries of our molecules and how reactions proceed. There's also another one that's a little bit more detailed. It's called molecular orbital theory. With molecular orbital theory, we don't really try to talk about the geometry. We really stop off at hybridization for that. But we look more deeply into the bonds and their properties. Okay, and this is the way it works. Remember how when we did our hybridization, the first thing we had to do was combine the orbitals. Okay? So, instead of combining the orbitals within the same atom, so the S's and the P's, we're going to combine the orbitals between two different atoms. Okay? Now they'd be different, but just two atoms, okay, to discuss and understand the interactions, okay? After we come up with our new molecular orbitals, and these are going to form molecular orbitals, okay? And just like if you start with two orbitals, you end up with two orbitals, remember the number of orbitals you start with should equal the number of molecular orbitals you form. Okay. After we get our molecular orbitals and we look at their energies, then we're going to fill the molecular orbitals with the electrons. So, you can review how we did the electron configurations. In electron configurations, we just looked at the energy and we were just given the S and the P and the D and the F. And in this case, once we start going to molecular orbital theory, and like we did with atomic orbitals for hybridization, okay, we made our orbitals first and then we filled it. Okay, so we're not given our orbitals, we need to make it. And then the rules that we apply for filling it, same as before. Lowest energy up, and then if they're degenerate in energy, then you equally distribute your electrons before you start pairing them. Okay, so let's take a look. This is what I'm saying we're going to do. Let's see how we do it. So, let's look at hydrogen. Okay, so if you look at hydrogen, here's my energy. If I have my two atoms, here's my hydrogen atom, and here's my other hydrogen atom, okay? This is basically non-bonding, just like you have your hydrogen atom all by itself. Let me draw it here. Okay, So when they are the same phase and you bring them close together, almost like a piggy, right? You bring them close together, then you form your sigma bond. Okay? So you bring them close together and you have basically your sigma bond. Okay? What happens if they're opposite phase? Let me give you a different color for that. If they're opposite phase, then when you bring them close together, this subtracts that out. And you get here what we call a node. Node, or you might hear, or nodal plane. Okay, and what this means is there's no electron density. Alright, and what we call this is we call it an antibond. This is high energy. And if it drops down, it actually increases the same amount of energy. So when we're done, everything stays conserved. And you put an asterisk next to it. This tells me it's an antibond. Alright, so I have a sigma antibond. So this is what happens when I have a 1s bond formation. You're going to have a sigma bond, and you're going to have a sigma star, an antibond. Now, what about these electrons? So, for hydrogen, the hydrogen atom has one electron. So when I look at my molecular orbitals, I have 2 electrons. I'm going to draw this just so you can see the symmetry of it. Alright? I have 2 electrons to play with. So with the 2 electrons to play with, I'm filling up my molecular orbitals. So we always put molecular orbitals. Just finish this thought. Okay. So molecular orbitals always go in the center. And on the sides is atom 1 configuration and atom 2. Okay, so we have a total of 2 electrons that we're working with, not 4. I have 1 from this atom, 1 from that atom. When I look at the bonding, I have 2 electrons in there. Okay, so we know then that since I'm filling up my bonding and not my anti-bonding, then hydrogen just has a bond between the 2 atoms. Okay, so before we move on to helium, let's talk about one other concept, and that is bond order. It's equal to 1/2 my sigma electrons, or bonding electrons. We'll get a pi. Minus 1/2 anti-bonding. Not but anti-bonding electrons. Okay, so for hydrogen, it's going to be equal to 1/2 of 2 minus 1/2 of 0. It gives us a bond order of 1. So for hydrogen, This is a single one. Okay, so far so good. All right, let's move on to helium.